Let me quickly mention a corollary of Minkowski's convex body theorem, which is an immediate generalization of the theorem to any lattice. So, corollary that B be a convex, measurable, subset in Rn, symmetric about 0. Suppose either the measure of B is greater than 2n, or the measure of B is equal to 2 raised to the power n, and B is compact. Then, for any unimodular lattice lambda, we have intersection of B with this lattice minus the origin is non-empty. Namely, this convex measurable subset B that is symmetric about 0 contains a non-zero element in this lattice. Here, by unimodular, we mean that the fundamental domain of this lattice has measure equal to 1. We can also say that the covolume of this lattice in Rn is equal to 1. Namely, there exists a probability Brown measure on this quotient space Rn mod lambda that is invariant under the translations in Rn. But this is not really the definition we are going to use. What we are going to use in the proof of this corollary will be that the matrix formed by the coordinates of this unimodular lattice under the canonical basis of Rn has determinant plus minus 1. That is what we are going to use. So you don't have to memorize this definition at this moment. You will see in the proof. So any unimodular lattice lambda has a basis written as script E sub I equal to A sub I1 E1 plus A sub In En, where I is from 1 through n. And E1 through E sub n is a canonical basis of Rn. Which means E sub I will be the vector where the ith component is equal to 1, where other components are equal to 0. And now suppose A is a linear transformation from Rn to Rn such that the action of A on those spaces is equal to, has a matrix representation denoted by this matrix formed by those coefficients. Namely, this is A11, AN1, A1n, ANN. And because lambda is unimodular, we have that the determinant of the matrix A is equal to plus minus 1. And in particular, the determinant being equal to plus minus 1 implies that this linear transformation is measure preserving. So the Lebesgue measure of script A inverse of B is equal to the measure of B, where B is just this convex measurable subset that is symmetric about 0. And moreover, you can easily see that B being symmetric and convex implies that A inverse of B is also symmetric and convex. Because here A is an isomorphism of linear spaces, you should be able to check this directly with linear algebra. And at the same time, this script A is also a homeomorphism between two topological spaces. So B being compact also implies that A inverse of B being compact. So every property of B will be preserved by A inverse of B, because A is an isomorphism between linear spaces and also a homeomorphism between two topological spaces. So those properties should be very easy for you to check. And now we are ready to use the Minkowski's convex body theorem, which tells you that A inverse of B contains a integral vector, say L1 multiple E1 plus Ln multiple of En. So those L sub i's are integers and L sub i's not all zeros. And now you apply A to this vector. It follows that script A applied to this vector will be in B by this relation. And the left hand side is equal to, by the linearity of A and this construction, L1 times script E, which is given here, plus L sub n times script E. And this vector on the left hand side is non-zero, and at the same time lives in lambda, because script E1 through script En form a basis of lambda. So this is in lambda. And we are done. This shows that lambda has a non-trivial intersection with B. By non-trivial, we mean that B contains a non-zero element of the lattice lambda. In the end, I would like to make a remark. Why do we mention this corollary? Although it seems to be very trivial. Actually, this corollary of the Minkowski's convex body theorem will be used in a small place of the proof of the Mahler's compactness criterion. In another video I made about the proof of Mahler's compactness criterion, we made a claim which says we're going to find a basis of any unimodular lattice that belongs to a given ball of radius that only depends on the dimension of the lattice and a given parameter s that is a radius of this ball centered at the origin. And we started the proof of this claim with the first vector, the first basis element. Back then, we used another argument to show the existence of such a B sub 1. But now we have proved the Minkowski's convex body theorem. And it follows from the Minkowski convex body theorem that the shortest vector in any given unimodular lattice is contained in a ball centered at the origin with radius such that the volume of this ball is bigger than 2 raised to the power d, where d is the dimension of the lattice. So the first step in the proof of this superclaim follows immediately from the Minkowski's convex body theorem that we just proved. However, if you don't want to go through the Minkowski's convex body theorem, I think this fact also works, which is easier to prove, as I did in the earlier video.